Hi everyone, welcome again to my home. It's a nice cool evening and really a lovely day here in Durham, North Carolina today. Maybe you can tell since my last tutorial I had a haircut, so I'm especially feeling the nice cool weather this evening, and I'm happy to spend a little bit of time with you talking about synaptic integration. So we continue to talk about our important core concept in the field of neuroscience that pertains to the communication that happens among neurons and between neurons and peripheral structures via the generation of chemical and electrical signals. Specifically, our learning objective today is to discuss the concepts of excitatory postsynaptic potentials and inhibitory postsynaptic potentials. And what I want you to be able to do is to be able to define these terms in terms of the reversal potential for the postsynaptic current and the threshold for generating an action potential. Now, I trust all of that will be clear as we go through the tutorial together. And secondly, my objective is for you to be able to describe how postsynaptic potentials can summate within a neuron, both in space and in time. All right, well, in order to address this shorter tutorial on this subject tonight, I want us to start by reviewing the mechanisms of chemical synaptic transmission. Now, you've had a few tutorials on this subject, so I think things ought to be fairly clear, so I'll go rather quickly through this. As you will recall, an action potential will invade the end of an axon where we find our presynaptic terminal, and a wave of depolarization then conveys positive charge along the length of this presynaptic terminal. And once that positivity reaches our voltage-gated calcium channels, they will open and calcium can rush into that presynaptic terminal. And calcium in the presynaptic terminal is the key trigger that leads to the fusion of docked vesicles, allowing their neurotransmitter to then passively diffuse out into the synaptic cleft. And I'll just remind you that this happens when calcium interacts with synaptotagmin, and that leads to a twisting and pulling together of that snare complex that results in the fusion of that vesicle with the presynaptic terminal membrane. And that fusion event creates a pore so that the transmitter can diffuse out. And then once we have a transmitter in the synaptic cleft, then that transmitter can interact with receptors. In this illustration, we have ionotropic receptors. And that's really going to be our consideration this evening. You will recall from past tutorials that there are also metabotropic receptors for transmitters that mediate longer lasting effects. And surely that's part of what we have in mind when we talk about the integration of postsynaptic signals. But for this tutorial, I want to focus on the integration of currents that are mediated via the activities of ligand-gated ion channels. And I want us to think about those currents that are more likely to lead to the generation of an action potential in this postsynaptic neuron as this wave of depolarization reaches that postsynaptic terminal. Or I want us to think about those conductances that might actually make it less likely for that postsynaptic action potential to be generated. Okay? So on the one hand, we're going to talk about action of neurotransmitters that elicits what we call an excitatory postsynaptic potential. And on the other, we're going to talk about activities of neurotransmitters that give rise to what we call an inhibitory postsynaptic potential. So forgive me if I use that jargon quite a bit today, EPSP and IPSP. This is jargon that we will find throughout the literature in the world of neuroscience, especially as it pertains to neurophysiology. So when you hear that EPSP, IPSP, think of excitatory postsynaptic potentials and inhibitory postsynaptic potentials. So I want us to spend just a little bit of time with what I consider to be a very important figure from the textbook that we've been reading along with this course so far. It's figure 5.21, and it pertains to these concepts of excitatory postsynaptic potential, inhibitory postsynaptic potential, and how we can understand and even define those terms relative to the reversal potential. Remember that concept? That comes way back when we first introduced the Nernst equation and talked about the equilibrium potential for a permeant ion. Well, we're going to bring back that concept and now apply it to the conductance that passes through a ligand-gated ion channel. So what we have illustrated in part A of this figure is an excitatory postsynaptic potential. So we might think of this as a postsynaptic potential that is secondary to the release of, let's say, glutamate from a synapse, or maybe a collection of synapses that are converging upon the same dendrite of a postsynaptic neuron. Well, as glutamate binds to its ionotropic receptors, for example, AMPA receptors, those receptors open and sodium rushes into the cell. And as a consequence, what we see is a depolarizing event. We call that depolarizing event an excitatory postsynaptic potential. So why do we call it that? Well, here's the definition. The reason why we call it an excitatory postsynaptic potential is that the reversal potential of the active conductance is well above the threshold for firing an action potential. Now, a couple of tutorials ago, we looked closely at the conductances that pass through the nicotinic acetylcholine receptor, and because both sodium and potassium can pass through that receptor, the reversal potential for the net current flow, that is the net conductance, was around 0 millivolts. And that's very much the same situation that we have here for this conductance that is gated by glutamate. So the reversal potential is about 0 millivolts, and that's because sodium is entering the cell through the AMPA ionotropic receptor, and potassium is leaving the cell. So the voltage, that is the membrane potential, at which there's no net current flow, is 0 millivolts. Okay, so what does that mean for this particular synapse that has this effect on this neuron? Well, what this means is that if this synapse, if this input to this cell in question from which we are recording, if this synapse could have its way with that neuron, and pardon me for that language, but I think it helps, if that synapse can have its way with that postsynaptic neuron, that postsynaptic neuron will be depolarized to the reversal potential of that active conductance. Now, the synapse doesn't have its way because it's, like most synapses in the brain, a weak synapse. Maybe there's not a lot of glutamate that's being released. Maybe there aren't a lot of AMPA receptors to receive that glutamate. However, the reversal potential for the AMPA-mediated conductance is near 0 millivolts. So that means that if this particular synapse could completely capture that postsynaptic neuron, it would depolarize it to the reversal potential. Well, as I just mentioned, most synapses are not that powerful. They're actually rather weak, and they typically only allow for a postsynaptic membrane to depolarize by a few millivolts. And that's the story that we have here. If there is a single active glutamate synapse, even a very strong and powerful glutamate synapse, we may only see an excitatory postsynaptic potential of some modest value. But if we imagine the concurrent stimulation of a number of inputs, we might very well have a depolarization that hits that threshold for firing an action potential. So do you remember what threshold is? Threshold is when more sodium ions are rushing into the cell than potassium ions are leaving the cell. When we reach that threshold, then an action potential can fire. Okay, so let's put this together now. So we activate a glutamatergic synapse, or perhaps a collection of glutamatergic synapses on this cell. The cell begins to depolarize because sodium is rushing in to the cell through the AMPA receptor channel, and its reversal potential is around 0 millivolts, so we've got a large conductance because the channel's open, and we've got a large driving force, right? Because we're pretty far away from that reversal potential when we start at rest. Well, as this cell begins to depolarize, now we start opening up our voltage-gated sodium channels. And that's what leads to triggering this action potential that we record here. Okay? So the binding of glutamate to the AMPA receptor is what gets us started, and then the action potential is generated through the usual means, through voltage-gated sodium channels, accounting for the sharp rising phase, and then sodium channel inactivation begins the falling phase. That gets reinforced with the opening, the slower opening of the voltage-gated potassium channels. All right, that is a typical glutamate synapse within the brain. Now let's consider a different neurotransmitter, the neurotransmitter GABA, gamma-aminobutyric acid. Now, if you remember, GABA binds to a receptor that's part of an ionotropic receptor, and that receptor is permeable to chloride ions. And in most mature brain cells, there's more chloride outside than inside. So that means when the chloride channel is open, chloride ions are going to want to enter the cell. Okay? And if we are making the inside of the cell more negative because of the influx of chloride ions, we might expect some hyperpolarization. And that's exactly what we see here. If we activate a GABA synapse, there may be a small hyperpolarization. And the reason is that we are trying to drive that postsynaptic membrane to the reversal potential of the active conductance. Same principle that we talked about for the glutamatergic synapse, only now we're applying it to the situation of a GABA synapse. So notice where the reversal potential is for this particular neuron in question. It's actually hyperpolarized relative to rest. So when the conductance opens, the concentration gradient is such that it will hyperpolarize by a few millivolts this membrane potential. That's what we call an inhibitory postsynaptic potential. Not because it's hyperpolarizing, but because the reversal potential is below threshold. All right, just to reinforce that point, let's look at the third example. This also is a GABA synapse, only because of the concentration gradients inside and outside this particular cell. The reversal potential for the active conductance is actually in the depolarizing direction. But get this, it's still an inhibitory postsynaptic potential. Why? Because the reversal potential of the active conductance is below threshold. Okay? I hope you're catching on to this. So again, let me use that somewhat loose language of saying if that synapse with that particular conductance could have its way with the postsynaptic neuron, it would clamp the membrane potential of the postsynaptic neuron at the reversal potential. Okay? No more, no less, at the reversal potential. So, in theory, the most depolarized this neuron, shown in panel C, could ever possibly get with this active conductance is the reversal potential, which is below threshold. So what we see, in fact, is when we activate that synapse, a depolarizing postsynaptic potential, but it's still an inhibitory postsynaptic potential. So please don't make the association of depolarization with excitatory postsynaptic potential, because you'll be missing the concept entirely. I want you to associate the idea that the reversal potential of the active conductance is what defines a postsynaptic response as being an EPSP or an IPSP. So if the reversal potential of the active conductance is above threshold, then that is an excitatory postsynaptic potential. If the reversal potential of the active conductance is below threshold, then that is an inhibitory postsynaptic potential. Now, if you're following along with the tutorial handout that I've given you, I'm asking you a question at this point. I'm asking you, can the same neurotransmitter give rise to excitatory postsynaptic potentials and inhibitory postsynaptic potentials? Well, the answer is yes, and the reason has to do with the definitions that I've just given you, which are illustrated over here in panel D. So if the difference between an EPSP and an IPSP is the reversal potential, then you should now have some intuition that tells you that the reversal potential is really a function of the concentration gradient of the permeant ion. So suppose that concentration gradient were reversed. Well, we may take a reversal potential that is above threshold and now place it below threshold, or vice versa. Well, this is the case for GABA. GABA is usually described as the principal inhibitory neurotransmitter in the brain. But about 10 or 15 years ago, we realized that this might not be the case in the developing brain, and here's why. When we look at the pumps for establishing chloride gradients in the developing brain, we realize that there is actually a difference. There's a bit of a switch that takes place during brain development, at least for most neurons in the model species for which this has been studied so far. What we find is a particular type of chloride transporter that is expressed in immature neurons, and then as these neurons grow up a bit, a different transporter is expressed, and that transporter reverses the chloride gradient. So in an immature neuron, we typically have high chloride concentrations in the cytoplasm and low chloride concentrations in the extracellular spaces. But once this gene switch is turned on and a different type of transporter is now inserted into the membrane as the neurons develop in postnatal life, now we have low chloride concentrations within the cytoplasm and much higher chloride concentrations outside of the cell. And this has a very predictable impact on the reversal potential of the GABA A channel conductance. The reversal potential in the immature neuron is above firing threshold for most neurons, whereas following the reversal of that gradient, as neurons get older and more mature, we find that the reversal potential for this concentration gradient of chloride now falls below threshold. So in the immature neuron, GABA is an excitatory neurotransmitter mediating excitatory postsynaptic potentials. But in the mature neuron, GABA typically is going to mediate inhibitory postsynaptic potentials. Okay, and again, the key difference is the expression of different transporters that can change the gradient for the permeant ion. Here's some electrophysiological data that makes this point. In the left part of panel C is a recording from a 6-day-old neuron in a mouse, and what we find is that with application of GABA, there is a series of action potentials that rise upon this envelope of depolarization. This is an EPSP leading to the generation of action potentials. Now, if we were to wait a few days later, as these neurons mature and apply GABA, now we see that there is a hyperpolarization of the membrane. And the difference is a pump that reverses the gradient from high intracellular chloride levels to low intracellular chloride levels across the first few weeks of postnatal life, at least in the mouse model. We have every reason to believe that the same biology is happening in the human brain during development. We just don't yet know exactly when that shift in expression of chloride transporters takes place. All right, now I'd like to switch gears just a little bit now and talk about the integration of both excitatory postsynaptic potentials and inhibitory postsynaptic potentials. And in figure 5.22, we see a very simplified representation of what we find in the brain. We have a postsynaptic neuron that's receiving a number of inputs. We're illustrating 3 of them here. So we have an excitatory input that we call E1, another excitatory input that we call E2, and then an inhibitory input. Now, of course, if we're talking about a typical brain cell, there would be thousands of these inputs, some of which would be excitatory, some of which would be inhibitory. But we're going to keep things real simple and only talk about 3. So let's consider what would happen if either that first or the second excitatory input alone were to fire an action potential. Most likely what we would see is a subthreshold depolarization. So that's what we have here if we activate either of these 2 inputs. We have a small depolarization of a few millivolts. And this really is more typical of what we see in the brain. No one synapse is that strong. So in order to achieve firing threshold for the generation of an action potential, we need to have multiple excitatory inputs summate their postsynaptic potentials in the same region of the dendrite at the same time. This is what we call summation. So look at what happens if now we activate excitatory input 1 and 2 concurrently. Now we can generate a postsynaptic potential that sums up. And the sum of these 2 potentials is sufficient to achieve action potential generation threshold. And as a result, we have this nice action potential that fires. Okay, well, let's now think about our inhibitory input that we have on this neuron. So let's imagine this is an input releasing GABA, and let's imagine it's a mature neuron. So when the GABA A receptor channel opens, chloride is going to rush into the cell, and that very well could cause a hyperpolarization of that neuron. And in fact, that's exactly what we see here. When we activate input I, the inhibitory input, we see a small inhibitory postsynaptic potential. And again, it didn't matter if it was hyperpolarizing or depolarizing, as long as the reversal potential of the active conductance was below threshold. It could be here, or it could have been here, but as long as it's below the threshold, then it will be an inhibitory postsynaptic potential. Okay, well, now let's get a bit more realistic. Let's have both excitatory and inhibitory inputs firing more or less the same time. And what we see is that these inputs will sum algebraically. So if we add one excitatory, one inhibitory input together, then the result is going to be the summation of the 2. And in this example anyway, we will see at best a subthreshold depolarization. That might still be the case if we were to add the 2 excitatory together with an inhibitory. So I think you get the idea here. That is that no one synapse is typically strong enough to result in the generation of an action potential in the postsynaptic neuron, but we need to have many synapses, perhaps even tens or hundreds or thousands of excitatory inputs converging on the same neuron at the same time in order to depolarize that membrane sufficiently to reach threshold. Because we can be sure that there's probably some inhibitory activity that's converging at the same time as well. So we have to overcome the impact of that inhibitory input, even while we summate our excitatory inputs to achieve threshold. I'm distracted to my left just for a moment. It sounds like a deer has just walked by. It's dark enough that I can't see him. Could be an opossum, but it sounds like a deer. Actually, I think it is an opossum. Well, this brings us to the end of this shorter tutorial, and I hope it helps you put these concepts of excitation and inhibition in context, and I hope it allows you to better understand the neurophysiology of real neurons in the brain. Okay, so when we talk next time, we will be exploring together the fascinating phenomena of synaptic plasticity. I can't wait to have that conversation with you all.